in the vapor pressure video, we looked at how external pressure affected vapor pressure and or boiling point, whichever way you want to remember it, because they all go together. But pressure also affects melting and freezing. And you will see different trends. Just right, water, it has to be unique. So for most substances, I'm going to have a trend here, but water is going to be kind of the opposite. So for most substances, the solid phase is more tightly packed than the liquid. Okay, this is kind of how we talk about the solid phase compared to the liquid, so that makes sense. The solid is more dense than the liquid. If you have a really high external pressure, that pressure, you can think about it like pushing down on the atoms and the molecules. It helps hold them together. So it would take a higher temperature to melt something if the pressure is higher, right? When you go to melt it, you're trying to unpack or like move apart those really densely packed and tightly packed molecules in the solid state. And if you have a high pressure that is still trying to like push them together as you do that, you'll have to put in more energy to overcome it. For water, it is the opposite. So in water, the solid phase is less dense than the liquid phase. And just to pause there, the solid phase is less dense. So there's more, I don't know, empty space in a solid piece of water than there is in a sample of liquid water. This all happens because of the hydrogen bonding in water, but we function as a species very well because this happens, right? This is why ice cubes float in your drink. Okay, that may not be vital to your existence, but this is also why when lakes freeze, they freeze across the top and they don't freeze from the bottom up, which is good and important because if they froze from the bottom up, all of the fish would die. So the ice forming on top and being on top of the water because it's less dense, right? It leaves the liquid water for the fish and also kind of helps insulate it so the fish stay alive in the winter. Um, okay, so because of that though, if you increase the pressure, we're pushing the molecules closer together. In water, that helps it melt. So for water at a higher pressure, you don't need to heat it up as much to melt it because the pressure will help push those molecules together and get it out of the solid phase. This kind of information, we can show it with a graph or a plot, and it's a plot that's called a phase diagram. It's pressure versus temperature, and it gives you a map that tells you which phase is the most stable at each pressure temperature combination. So I'm going to give you the details of what all the different pieces mean, but then we will look at the pictures because that's the important part. That's the thing that's going to communicate a ton of information in one step. So on a phase diagram, you will see lines that are called phase boundaries. It's a line that tells you the pressure and temperature at which phases are in equilibrium. So that seems, I don't know, maybe ominous depending on how you felt about equilibrium when we did it. But if we look more closely, you'll be able to put some more phase transition words to it. So there will be a line that separates the parts of the diagram that have the liquid substance and the vapor substance. So this liquid vapor line, you can use it to find the vapor pressure at any temperature, or you could think of it as telling you the boiling temperature at any external pressure. So along this line, it will tell you if the external pressure is this is what my boiling temperature is. Or if this is the temperature that I'm at, this is what my vapor pressure would be. The solid vapor line gives the vapor pressure of the solid at any temperature, or it's the sublimation temperature at any external pressure. So, right, solid vapor, you've got solid on one side, vapor on the other side, it will tell you these values. The solid liquid line gives the melting or freezing temperature as a function of the external pressure. And this is where you will find a difference between something like water and any other substance. So for most substances, this line will lean to the right. So what that means is as the pressure's increasing, which you'll see this on our picture, pressure's on the y-axis, as the pressure goes up, the temperature goes up, the line leans to the right. For water and any other substance that has similar properties to water, the line leans to the left. As you go to a higher pressure, the temperature goes down, which results in this line that leans to the left. So these three lines are on here. There are 2 points that show up. One is where all of these lines intersect, and the other is going to be at the end of the high pressure, high temperature region. So where all of the lines come together, this is called the triple point. And it's the point at which all three phases are in equilibrium. So if you are at the triple point, you have solid, liquid, and gas all in equilibrium with each other, right? That pressure temperature combination gives you all of the phase changes at once. Below the pressure of the triple point, the liquid cannot exist. So when you see the triple point on there, that's the lowest pressure at which you can have a liquid. The other point is called the critical point. This is when the pressure and temperature are so high that you have a new type of substance. It's a high density vapor, low density liquid that combines, it turns into one phase that we call a supercritical fluid. If you are above the critical temperature, the liquid cannot exist. So this is kind of your absolute limit for, I have a liquid at this high a temperature, but the pressure is also increased to kind of push all of those molecules together to make sure they stay as a liquid. And where you end up is in a totally new phase. Supercritical fluid, it's really cool. It's weird to think about because it's unique from a gas or a liquid. It kind of has properties of both. Carbon dioxide in supercritical fluid form has become really important and environmentally friendly for doing things like dyeing materials or creating decaf coffee, because you can use supercritical carbon dioxide to dissolve the caffeine in the coffee bean and then also just get it to like float away when you're done. You don't have any liquid to dispose of. There's no like toxic solvent that you have to worry about, and there's no residue left on the coffee. Okay. I'm going to draw a phase diagram for water and point out a couple of features. So we have pressure on the y-axis, temperature on the x-axis. So on the y-axis, I'm going from some low pressure to some high pressure. For water, just a regular linear scale here is fine. And I'm going to mark off 1 atmosphere for a pressure reference point. On the temperature side, right, I've got something below the freezing point, something above the boiling point, and I've just got 0 and 100 degrees marked on here. So the lines that we have a line that it kind of, I guess this whole thing kind of looks like a Y, and it's dividing my diagram essentially into 3 sections. And those sections are the solid, the liquid, and the gas. So at low temperature for most of the pressures, I have a solid. For a wide range of temperatures, but very low pressure, I have the gas. And then the liquid, if you only have these three sections, the liquid is always going to end up in this kind of middle of the Y section. I also have some points labeled here. So I've got my 1 atmosphere mark going all the way across. And so the C and the D point labeled there. Obviously, I should do A and B first to tell you what it's about. A, well, if you look at it, I've got the lines that show between my liquid and my solid, right? That's a phase boundary. I've got a line between the liquid and the gas and a line between the solid and the gas. So A, where all of them come together, that's the triple point. B is my critical point. And so beyond B is where the supercritical fluid, like that's where that state exists. So I've kind of got some dashed lines. These dashed lines are usually not drawn in, but that's what that means. So that line ends at a point. If you extend it up and over, everything that falls into that section would be supercritical fluid. Point C, well, this is liquid and solid in equilibrium at 1 atmosphere. That hits at 0 degrees Celsius, which, since we know the properties of water, this kind of helps make the reference, but I'm at 1 atmosphere, line between liquid and solid. This is a freezing point, but because it's at 1 atmosphere, it's my normal freezing point. And then, right, continued across still at 1 atmosphere, the line between liquid and gas, the point on the line between liquid and gas at 1 atmosphere, it's a boiling point because I'm going between liquid and gas, but it's at 1 atmosphere, so it's my normal boiling point. All right, and then notice that for my liquid solid phase boundary line, this is for water. As I go to a higher temperature, this line leans to the left. So this is what I mean by leans to the left. Higher pressure means a lower temperature for melting. Whereas something like carbon dioxide, so I also have this phase diagram written, carbon dioxide, so I still have pressure versus temperature. So I still have this like Y shape, where at higher pressures for a lot of temperatures, I have solid. For a wide range of temperatures, but low pressure, I have gas. And then there's this in-between section where I have liquid, except you'll notice some differences compared to water. So when we think about carbon dioxide, I mean, probably you just think about it being a gas because that's what it exists at 1 atmosphere, at most temperatures, right? You have to get really cold to freeze it. In fact, we can look at the phase diagram to see what temperature it would freeze at. So I have this Y shape. I have my triple point marked on here where the 3 come together. The thing is, like, because it's a gas at so many pressures, in order to display this, to see the range of states for carbon dioxide, my y-axis is exponential. So I have 1 atmosphere on here, but it's really low on my y-axis. I also have 5 atmospheres and 73 atmospheres labeled. At 1 atmosphere, my line between solid and gas is at negative 78 degrees Celsius. So at 1 atmosphere, we only go through the solid gas line. So what I have at point C is a normal sublimation point. Well, I mean, I skipped A and B, but those are still, A is the triple point. So I would have to be at 5 atmospheres to have liquid carbon dioxide. So we have to get to a pretty high pressure to use carbon dioxide as a liquid, and especially, as we're going to see, as a supercritical fluid. The critical point is at 31 degrees Celsius. Okay, that's not super hot, but 73 atmospheres of pressure. But that is the point at which we can get this into a supercritical fluid and then use it for all of these applications that we have seen. Also, right, the thing to note about the solid liquid line for water, we saw the tilting left. You can see the tilting right here. So carbon dioxide, like most substances, as you go to a higher pressure, those molecules that are already tightly packed, that pressure is helping to keep them together. So you would have to go to a higher temperature to melt it.